All right. So welcome to what I think will be the last Twitch lesson for this fall for us. Um, Obviously the title's autonomous, but I'm actually gonna stop for a moment and ask everyone, how PID tuning went since last week. Yeah, depending on how many people are here, even. It looks like people are. Oh, I had trouble finding where you got that program. It was in the slideshow that I linked, that I shared with everyone. Be sure. Hold on, let me get this off the screen so I don't show all your emails. Vast last meeting. Oh, but let's see. So, like this program, like the code or Visual Studio Code, because if it's just the this, well, it's linked in the document. If you're talking about Visual Studio Code, it's a bunch of Java codes. Um, you mean this just in general or the project itself? Because if you need the like this program is what we call an IDE or integrated development environment. It's here if you need it. And you'll probably want the Win64 version, Windows 64. But anyway, so yeah, whenever you can, just play around with that. Again, we have Slack, so if at any point you're working through any of this stuff and you have questions or you can't find something, like just annoy me on Slack or group me, either one. Anyway, um, autonomous. What's autonomous? As you saw, countdown the first 15 seconds of the match. Don't have any driver input. You know, they said every match, drivers behind the line, 3, 2, 1, go. That's because we can't touch the controls for the first bit of the match. That's the autonomous period. It's usually 15 seconds, but that's not always a given. Usually there's bonus points on offer during autonomous. 2018, the bonus was oddly enough, like on the surface, it didn't look like it was super worth it, but then you realize that you could take control of things early, and so a lot of the autonomous scoring just happened in Taliop. After that, the driver controls the robot until the end of the match, and that's the Taliop period. Even though this whole lesson's titled Autonomous, I'll talk about Taliop a little bit because we reuse a lot of what we do for Taliop in Autonomous. So in Taliop, you read inputs from controllers. If you've seen the screen of the driver station, I have the 2022 beta driver station here. That's why the version number may look a little weird. But you know, 1, -1 for your axes, for your analog inputs. All your digital stuff's here. You've got a POV hat. You can send a rumble to the controller. You know, you take that code, and if you go look at our, let's see, robot.java, and you go down to manual control, you can see where, you know, this control board object reads from the controllers. So a lot of these are just checking like those controller axes and buttons. And then we're just calling, you know, commands, or not even really commands. We're like setting what we want subsystems to do if they can. Now, note it is totally valid for a subsystem to get a, you know, request for something and deny it if it's going to tear up the robot. So, or, you know, for it to decide, oh, I have to move something else out of the way to get this done. That's kind of why it's a want shot instead of just set shot. Um, yeah, so this link here is what I was just looking at Visual Studio Code. Back in 2018, we had an OI object that kind of is maybe even a better example for this because here you can see like DC and OC are driver controller and operator controller respectively. And so it's like you know, if we get the left bumper button on the operator controller, that is to spit out. So operate intake 1, 1. Yeah, whereas button RB is spit out. Oh yeah, so we can intake from the operator controller. Driver can spit out the cube. Driver has various powers at which they can spit out the cube with different buttons. You know, different like go to bottom. These are all lift set points. Um, yeah, and it's just in general, we check for buttons and then do something based on the button. And you know, we've got a little bit of like latch logic in here and among other things, but you know, it's very much just check button, do thing. If button, do thing. So, actually, let me go back to where that was. So notice that, we have all these methods to do things in the subsystems. Because we talked about subsystems before, and, you make methods so that both teleop and autonomous can control it. Lift climber, add power. Oh yeah, these are like, the lift control. Oddly enough, our lift wasn't going at full power because we'd smoke motors if we did, etc. Autonomous is we write action objects to call the same methods that we use for teleop. You know, these actions then get used in our autonomous mode objects. So an action is just like a singular thing like intake cube or intake ball or intake donut for storm surge, or set lift to angle, set lift to winning scale, or neutral scale height, or um set hook, set want shot autonomous midline, stuff like that get called in the mode object. So we'd have like, an example for our 2020 code. We'd have somewhere in here. Oh yeah, we had a launch action, which is, we initialize it with the shot object that we're going to use. This could be like the midline auto shot, and a timeout for how long we want to spend shooting. And this would call the same, set want shot button that you look in our manual control method. That's the same method that we use in teleop. So what do these actions look like? So the actions are just there to call the same subsystems we use, methods that we use for teleop, and keep track of if the task has been completed. Here's an example from our 2018 code of, every action has to implement start, update, done, and is finished. So done is like what runs after the task has been finished. Is finished is just something to check if, what's been asked to happen by the autonomous mode that calls this has happened. For example, and this is at position is just looking at the lift encoder to make sure that we're within a certain range of our target height. Um, it might make more sense later. I'll actually show how this stuff, like an example of this stuff running. So, actually. So for example, what will happen is when this action starts running, start will get run, and that just calls the, hey, do the thing. Update doesn't do anything because for this, we didn't need to keep giving it, telling it to keep going to the same set point. When it's finished, just check the encoder position. We had this instant finish option to where, like, if we didn't care about the lift getting to a certain height before the next actions run, we could say, basically what would happen is the start would run and then its finish would be true, and the mode would be able to continue to run. Yeah, that might make more sense when we actually look at the mode. And then here's just a more complicated example of like our intake action is actually using a circular buffer to like prevent against jams. So this is more emulating like what a human driver would do, where if they like notice that the cube jams in the intake, to let off the intake button and let it unjam. But these actions, a lot of them are very simple. A lot of them, but they can get very complicated when you're trying to do fancy stuff with them. And auto mode base is the base of our modes, and there's this run action function that every auto mode base inherits. And so this code is what runs this run action. Not super important other than just if you want to see kind of how our auto modes are working under the hood. That's it right there. So autonomous modes. I'm kind of going to throw you all off into the deep end here by just going with probably our most complicated auto mode ever, which is back from the 2018 year. But it has, but the reason I'm using this is it has everything. It's got, just, actions running one after the other. It's got the series action, which contains more actions that get run in series. We've got run action at Y, which is like a trigger action that waits to run this function until we're at a certain position. Parallel action, runs multiple things at the same time. Oh yeah, there's a run action at lift height, which is another trigger that takes a different action, and it will run this spit out cube once the lift is at the right height. So what I'm gonna do, get this up on the left, get that out of the way. No, I don't want you to default right now. Get that on the left side. Get the themes window out of the way. So this year there were for any given autonomous, there were multiple you know what, I'll just pull up a video. It's easier to explain. Ready. So our robot 1806 is up in this top corner. What happens at the start of the match is which side of these scales or switches are yours get randomized in this game. So our robot doesn't know which side of the field is it's to score on until now. And if you see this game data.car at 1, that's the second character in a string that we get handed by the field at the start of the match and power up. And so the second character is it'll be R if you get right scale or L if you are left scale. So at this moment, we are blue. Since the side closest to the camera is red, we know that blue is on the left. So first thing that happens in this autonomous mode is, we do some basically inconsequential stuff here. Oh wait, we actually print out the game data, I think, or get the game data and then check it. In this case, the scale would be left, so we jump clear down here. And we actually print out left. That was actually a kind of a receipt for us, because sometimes the field would mess up and tell us the wrong scale side, so we'd have to go bargain for a replay due to a field fault. So anytime we're dealing with game data, we need to print it out for our own records so we can go, question box it if something gets messed up. So after that, we do some setup. The safe side is just our left side path that goes from here to here-ish. Right where that white line is. So we set up that path. We set this reset pose from path action just sets the robot keeps track of its current position. we're basically taking the start point of this left path and using it as our current position, because on boot the robot thinks it's at 0, 0. This just sets it to the start of this path, because we know pretty much every match we started like right here, or right here if we were on red, but right here on blue. So we set that up. First thing, so yeah, we reset post and path action. That happens almost immediately. And we immediately run an action that's a parallel action that contains a series action that, and another few things. So this parallel action, arrays as list, is just that is just code to make a list of actions that this run action can handle. The parallel action will run this series action containing a few more things that will run in a series, as well as these things all at the same time. I don't know why switch to low pid was in a parallel. That really should have been in a series. But to be fair, the code worked, and this way it's just had a little bit of extra processing overhead. So I guess don't mind me explaining that there. But so you see how it like immediately lift to teleop hold. So the series action here has these two things in it. So lift to teleop hold immediately runs and completes, because our grabber would drag the floor if we didn't do that immediately. So it picks our lift up off the floor, and then the series action for the rest of this until we get to about here-ish, we'll just be waiting to uh, spit out the cube. Because back here in this parallel, running at the same time as this, we're running a drive path action to go from the wall clear over to here. And then this run action at X until we get 100 inches away from the wall is waiting to put the lift to high scale position. So at about here, so about there, that triggers and runs lift to high scale to pick the lift up off the floor. Well, not off the floor. From our teleop hold height, clear up to as high as our lift will go. So it lifts it up. And then as we're getting close to here, we're getting close to that 258 number, which is like basically as soon as our bumpers break the plane of this white line, and we spit out the cube. Once all this is completed, so that's completed, the lift to high scale is completed, all that, this whole thing completes, and then we we run an output time action to let ourselves know like how long it took to score the first cube. That's just for our own optimization purposes. That's not something that you have to do, but I highly recommend having some just, break points in your auto so you can see like, oh, hey, we finished the left side at this time. So as you can see there, I probably should have ran that. So I'm actually going to back up and replay this in slow motion. So you can see it lift up. Actually, let me go full screen. I'm going to mute this because that is really annoying to listen to. So, see, the match starts. We pick our lift up, run forward, hit 100 inches off the wall, start lifting our lift up, gets the top, we start scoring, and then lift to bottom, true, instant finish. So we don't care exactly when we get our lift to the bottom, we just need to get it to the bottom, and the timing was inconsequential, so we just said go for it. What's happening there is we do a turn towards point action to turn the robot around to turn it towards that cube. So, that runs. And then while our lift is even still coming down, we start this, finish turn. We do a new action, a new parallel action that contains an intake cube and a drive path action. So this whole way back to this cube, we're running the intake. Left side scale part 1, that's just a path from, back to where it was after it finished the turn to into that cube. We're just driving into the cube, running the intake the whole time. It's going to get a little hard to see. And so that intake action doesn't finish until the cube hits a sensor in our robot. So we're still driving into the cube, intaking it until it finally kind of snaps down into position. Kind of there, it pushes, and then that completes. Next, we do a drive path action to go back to the scale in a parallel. And we do an instant finish. Like basically, as soon as we have the cube, we're moving our lift back up to score. So all that's running in parallel. We're driving, we're lifting, and then once the drive path, since the lift to high scale like finishes immediately, as soon as this drive path finishes, we jump on to the next one, which is a turn towards point to turn back to the scale. We got this run action at angle range trigger that once we're within an angle of -50 to 10, we spit out the cube. So we spin back around, and as soon as we're in the angular range, we launch the cube. And because that takes like 0.1, the number on these spit out cubes, the number in parentheses is the time, how long we spit out the cube for. So 0.1 second after we spit out the cube, we immediately pretty much do what we did the last time, which is lift to bottom, turn to point, except we're turning towards this second cube here. Get to the bottom, drive path action, drive over with the intake running, and we run out of time in auto. But we do have the cube in the intake at the end of auto, kind of. We kind of silly in a showcase of extreme silliness, we immediately drive away from the cube and teleop. But that's the driver's problem, not the programming. We can't program the drivers to be smarter than the robot sometimes. And so you can come up here and see the R scale. It's a lot of the same stuff as the left side. It's just we run some different drive paths. But a lot of it is our robot's over here. I'm going to mute this to not get it, but I'll just run this in slow-mo just because it's kind of impressive, like all the things that our robot is doing at once in auto in this match. Like you can see really well here where it picks up the cube off the floor immediately. So immediately picks up the cube, starts driving. Just a note about path planning. This is a corner that we have to make with the robot. You want to get as wide out here as you can and take this as wide as you can to be able to carry as much speed as possible. This year, while we didn't have necessarily the best throughput on cubes to the scale on the close side, we were probably one of the fastest robots to get to the scale on the far side. Like we're really close to this other robot in time, and we had to drive clear across the field to get there. But yeah, so a lot of the same stuff. We go pick up cube number 2. Gets in our intake. Our intake detected a bit of a jam there. Our sensor wasn't calibrated right. So it's sitting there fighting with the intake a bit until it actually triggers. Back up. Lift and turn to point. Until the lift's at a height where we can spit it out. And then I think we do some acrobatics. And, oh wait, that's teleop. Never mind. The acrobatics were teleop driving, not autonomous. Anyway, so I know that's a lot to take in. Does anyone have any questions about like kind of like what autonomous code looks like and how we would do certain things in auto, because it's basically just finding creative ways to call your teleop stuff. Aside from pathing. Pathing is the main thing that's pretty much auto only. And we'll get there in a minute. Yes. So every year the rulebook will have like restrictions on where your robot can be placed. For 2018, you had to be against the wall. For 2019, you had to be on like the little platform things. 2020, you had to be on the like initiation line. But usually you can choose where on that line you can start. Like, for 2018, we set up to where we pretty much picked the same spot every time with few exceptions. Yeah, 2018 season. There was one auto that we had where we didn't do that. That was kind of a special case. We were with an alliance partner that had a 4 cube auto. So we had an alternate auto where we started right in the middle. We just lined ourselves up with this like tape here. And we ran this auto while our teammate did, you know, our teammate failed their 4 cube auto. But, in spite of us also missing cubes, I don't know why I picked a semifinals match. That was a bad semifinals match. Let me pick a more fun match to watch. But yeah, so we either started in that left corner or right in the middle. But, we had a strat, but that was all strategic stuff. Also, that intake you guys are designing for Storm Surge may look familiar. And for some reason in Teleop, our lift dropped down. But yeah, so if we make an intake that can pick things up, we can do more than just scoring our preload next year, hopefully. So yeah, did that answer your question? Okay. So drive pathing. Boy, is that a long explanation. So since 2018, we used adaptive pure pursuit. For some reason, it didn't work very well with our 2020 robot. I have many theories. I'd like to try to get that working preseason this year, but I don't know if we'll have time to do it. But either way, I'd like to just have either the practice robot from last year or something like available day one of build season at least to just immediately start running drive pass. Um, there's a link in the presentation to a really good PDF that explains adaptive pure pursuit probably better than I could. I'm just gonna open this document because I know it's the same thing. Um, you all who are here should read this because it is what our like that pathing code you saw the 2018 robot running is this stuff. Like the odometry works pretty much the same way. Path generation is pretty much that. curvatures. You know, so we set acceleration limits so that the controller doesn't tell our robot to do things it can't do. And look ahead point. But pretty much, we have a path that is just like you know XY coordinates on the field. And you can even see like that is the 2018 field right there with distances in inches, I'm pretty sure. And yeah, that's we control the robot to follow these paths. Um, so adaptive pure pursuit. Let me just break down what this means. Pure pursuit is just like pretty much trying to follow the path by looking ahead and trying to find, trying to control the robot towards that. Adaptive just means that the look ahead distance can adjust. But other than that, don't get too bogged down in the algorithm parts of this unless you want to. But because we have like code libraries that do a lot of this stuff. But also, with the odometry, that means we know our XY position on the floor, and that's how these like the run action at X works. Is run action at X just puts a like trip line on the floor 260 inches away from the alliance wall, that when our robot realizes that it runs over, the 260x trip line, we run this action. Does that make sense? And then I think a lot of you have seen it. But we do have cheesy path, like, and we can generate points in here. Because we didn't implement this all ourselves. We borrowed it from Cheesy Poofs. We can just change the background image on this every year to suit the game, and as long as we scale it correctly, like if we wanted to go from, say we're on blue, $30? Yeah, 130 is about right. 130. I'm gonna delete all these other points. 130, like, no. And 250, like 235, somewhere in there. So I'm gonna have to refresh that because I entered in a number that's way too big and it's gonna crash things. I should probably rewrite the. I should probably. Or actually, one of you should probably do some validation on these XY values and make it to where large values doesn't just crash it, it just ignores it. That would be really great. Oh yeah, and you can edit this to where like the robot's like bumper size is reflected accurately. I'm just gonna make this one on screen just because. So yeah, if you wanted to say go collect some extra power cells, assuming you have a functioning intake, I guess you could do that with this. You can adjust your speed. This is in inches per second. So like if you want to go 80, and you can even radius your points. Like see how it smooths that out so the robot can carry more speed because it doesn't have to go clear to a corner and stop. It can kind of breeze through here. And like that's it even turns it into some code that you can copy paste into a path. Notice that all the imports are for Team 254. We would need to like change all that, and it's for their 2017 robot even. But we could actually, if we really wanted to, we could actually change this template to where it could work in our own code base just like immediately. Oh, and I guess this would be reversed because we'd be driving backwards usually because the front of the robot would be pointed towards the goal. So anyone wants to play around with paths in our 2020 2021 code, they're free to do that. Um, Other than that, I don't know much else. Um, Sometime we need to. I don't want to do that. I want to do that. Sometimes we need to, if you've seen the like to-do list that we've got in Slack and Drive, someone needs to go start and make the 2022 storm surge repos. Uh, this is kind of much of a to do for me as you guys. We need to like figure out how to rewrite our code to where we can do some simulation stuff, so we can test things like pathing and lift PIDs and all that before we get a robot. We need to strip down the 2020/2021 practice bot so we can strap mock-ups to it or run paths with it early next season. Oh yeah, we need to continue working on Storm Surge. Our current progress on Storm Surge is not a whole lot. Like we have last I looked, we have a frame. Yeah, like last I looked, we have a drive frame. Um, got some bumpers, which is good. Um, we've got like half an intake that no offense to Kevin. Yeah, I'm just talking about like this as a mechanism. I'm not 100% sure how we would make this. I mean, it's 1.5 by 1 aluminum. Like, do we even have any of that? Like, and concept, this is good. This looks like it'd be incredibly sturdy. I'd worry about that being a pinch point, but you know, This is just my personal preference, but I'd probably just design this as like a couple of plates with some churro standoffs. This also looks a little heavy. Yeah, it is an easy adjustment. But, the idea of, having the wheel captured by some bars or plates with a shaft running through it, and, you know, especially if you're not going to run um, two bearings in each of these, I'd probably just go with plates. Other things to look at for drivetrains, citruscircuits.org/ like our robots. You can actually see resources, our robots. You can actually see like Citrus Circuits, like old robots, and you can see their frames. So if you're having trouble like designing a frame, if you're gonna copy someone, copy Citrus Circuits or Cheesy Poof's website. Go there and you go to first. Like they've got like all their robots listed out here. Like for example, like you could just go to their 2020 robot, and Cheesy Poofs makes what's called a technical binder. It's a PDF like explaining their entire design process, like why they wanted to do what they did. You know, strategy decisions on why they did what they did and why they built what they built. And they also have pretty detailed CAD images of like their frames. You notice their battery box and Citrus Circuits 2019 battery box are very similar. It's almost like they're using basically the same design with slight modifications. Anyway, students have any questions, I'm happy to answer them, and otherwise I don't have anything else. Also, geez, that's a 6 Falcon drive. They don't even talk about 6 Falcons is a lot. Nothing comes to mind. Well, since Nathaniel's the only one who's been active in chat, I think we can call that a meeting. If anyone else has any questions, feel free to annoy me on Slack. Or, I mean, you're not really annoying me. I'd rather get questions now than, you know, you know. If you have a question, ask before the season, please. Not that you can't ask in season. It's just I'm anticipating that I'm going to be getting a lot of questions in the season. Anyway, have a good week. See y'all in person tomorrow.